Today we're going to start our topic on sequences. And I know you looked at these in Algebra 1, so we're going to take a look at them again, maybe take them a step further, kind of refresh ourselves with some of the notation that we see. The big thing that we need to keep in mind here is a sequence is defined as a function that has its domain as the set of positive integers, meaning starting at 1. That's something that you really want to keep in mind, because a lot of times we think maybe we can start at 0, but it's going to be the set of integers, meaning your starting value will be 1, different from what we would say a lot of times with initial value being 0. Starting value here in sequences is 1. Okay, so we have a sequence is defined by this equation, and we're going to find the first 3 terms of this sequence. So take note of how we're doing this. We're finding this first term, a sub 1, meaning my n value here is 1. So in order to find a sub 1, I have to do 2 times 1 minus 1. Okay, 2 times 1 is 2 minus 1 gives me 1. So I know my first term here is 1. Now my second term, a sub 2, keep in mind n is now 2. Okay, so that's going to say I need to find 2 times 2 minus 1. So 2 times 2 gets me 4. 4 minus 1 gets me 3. And a sub 3, keep in mind if I'm doing that, that means my n value in that formula is 3. So now I have 2 times 3 minus 1, which when we simplify gets me 5. Now it's asking us for which term has a value of 53. Well, that's saying to us, so we know another way to write this, a of n is equal to 53. So if that's the case, this is one of those if they're equal, set them equal, and then we can solve type problems. And if we solve for n, we're going to find n in this case is 27, meaning the 27th term. Why will there not be a term that has a value of 70? Well, let's try it. Let's see what happens. Okay, so same idea. It would be like saying, let's set that equation equal to 70 and solving. And so if I added that over, this would give me 71, sorry. And then to divide through by 2, and it shows us that n would be 35.5, but it's not an integer. Okay, n needs to be an integer, right? And 35.5 is not an integer. Okay, sequences can also be described by using recursive definitions. So recursive, a sequence is recursively defined. Terms are found by operations on previous terms. Meaning, if I wanted to find the 72nd term, I need to know what the 71st term is in order to solve. Okay, so here's a recursive formula. And anytime you're doing recursive formulas, you always need to know the first term, and that's what they have told us. Okay, so I know my first term is going to be -2. So we have to find the first 5 terms of this sequence. So we already know the first term is -2. Now I'm looking for my second term. Okay, so keep in mind, that means, again, n here is 2. So in that equation, when we plug this in, I have f of 2 minus 1 plus 5. So this is saying to us, this is really saying what's the function at 1 plus 5. Okay, well, the function at 1, we know back here is -2, so I have -2 plus 5. So now we know that the f of 2 is 3. Okay, so we have the first 2, we got to find the first 5. So we're on to the f of 3. And again, keep in mind, this is now saying your n value is 3. So we have f of 3 minus 1 plus 5, which says I need the function defined at 2, and then I'm going to add 5 onto it. So the function defined at 2, we found back here, that was 3. Add on 5. And so we now, our third term has a value of 8. Okay, in order to find the next term, the fourth term, keep keep in mind that means f is 4. We're going to plug in. So if I'm looking at this, it's always doing the term before. That's that recursive idea. So if I'm finding the fourth term, that means I'm going to take the term before it, the third term, and add on 5. So our third term was 8. And I'm going to add on 5. So that means my fourth term of this sequence is 13. Okay, and my fifth term, again, so that means your n value here is 5. Because it's recursively defined, I know I'm going to need the term previous plus 5. So the term previous is 13 plus 5. That's going to give me a total of 8. It says determine the value of f of 20. It says think about how many times you've had to add 5 to negative 2. So if we're thinking about this, each time I'm doing this, it's always like 1 less than. So again, if I'm finding the fifth term, I had to have the fourth term plus 5. I'm adding that 5 on 1 less than. So if I'm trying to find f of 20, that means I must add 5, a total of 19 times. Okay, so the f of 20. I could think to myself, well, that would be the first term that we had, but I have to add onto that a total of 19 times 5, or 5 19 times. Okay, and by doing that, we would get the value of 93. So what we kind of just did there is we were able to come up with what's called an explicit formula. We're going to get into that a little bit more. We're going to come up again with the recursive definitions. Remember, defining the sequence in terms of the term before it, okay, for the sequence shown. And we're going to include a starting value. So we can see here our starting value is 5, so I know f of 1 is 5. Anytime you're writing a recursive sequence, you always need to have that starting formula. So f of 1 is 5. Now, we can take a look and try and find some patterns. To me, I'm looking at 5 times 2 gets me 10, and I can see 10 times 2 gets me 20, and 20 times 2 gets me 40. That's starting to build this idea in my head here that if I could have the term previous, and again, think in notation how we make that, how we can say that. I need the term previous, n minus 1. If I'm trying to find the third term, I need the second term. But then what have we done to each? We've multiplied them by 2. Okay, so your recursive, you're always going to have something recursive is going to be n minus 1, meaning the term before it. So again, if I wanted to try this out to find my second term, we could experiment, and I could say if I wanted f of 2, I need the term before it times 2. Well, f of 1 is 5 times 2 gets me 10. So that looks like that's good. And again, I would recommend trying a couple more, but I'll let you try that on your own. Okay, for number 4, the recursively defined sequence is given to us. So again, telling us about the term before it. And again, you can see here, we're given t sub 1, meaning our first term. You always need that. So we have to find the value of 4. So in order to find the value of 4, I need to know what 2 is and 3 to get to 4. Okay, so t sub 2. Again, let's think what that means. That means your n value here is 2. So if we plug that in the formula, that's saying we're going to have t sub 2 minus 1, and we're going to square that, and then add on 2. So 2 minus 1 is 1. That means we're taking our first term, squaring that, and adding on 2. So our first term is 2. We're going to take 2, square it, and add on 2. 2 squared is 4, plus 2, we get 6. So our second term is 6. We're looking for our fourth, so that means I got to find my third. In order to find my third, n is 3. In order to find my third, I need to have t sub 3 minus 1 squared plus 2. In other words, I need the term before 3. I need the second term. I'm going to square that and add on 2. So my second term was 6. If we square 6, we get 36. And add on 2, we get 38. so now we're coming up to our final answer of t sub 4. So again, n is 4. And if I'm going to try and find t sub 4, think of the patterns that we've just done. I want the term before. We're going to square it and add on to. Okay, so the term before was 38. We'll square that and add on to. So that brings us to having t sub 4 being 14. 46. Okay. One of the most well-known sequences is what's called the Fibonacci sequence, okay, which is defined recursively using this time 2 previous terms. So here's our definition below, and since we're using 2 previous terms, notice they had to give us the first, this time, 2 terms. Our first term is 1, and our second term is also 1. So we're going to try and generate the values for 3, 4, 5, and 6. So again, like it's saying in other terms, the next 4 sequences. And sometimes when you do this, you can start to find patterns and see what happens. You always want to look at patterns when you're doing sequences. So for that third value, n is 3, according to this formula, it says we're going to take f of 3 minus 1 into that f of 3 minus 2. In other words, we are going to take the second term and we're going to take the first term and add them up. Okay, so the second term is 1, the first term is 1, and if we add those up, we get 2. So our third term now is 2. We're going to find our fourth term. So again, n is going to be 4. Plugging into the formula that says we're going to find 4 minus 1 plus 4 minus 2. So think about what this is. 4 minus 1 is 3. I want the third term. 4 minus 2 is 2. And the second term we're going to add. Okay, so the third term we found was 2. And the second term is given to us, that's 1. So for my fourth term, I get 3. So it's looking like we're constantly adding the 2 previous terms. So let's try f of 5, and then maybe we'll take a shortcut for f of 6. So again, n is 5. Saying we want to find 5 minus 1 or 4 plus 5 minus 2 or 3. So again, in order to find the fifth term, I need to add the 2 previous terms. So my fourth term is 3, my second term is 2, and if I add those up, I get 5. Okay, so trying to take maybe a shortcut, now that we're finding that pattern for f of 6, thinking to myself, okay, to find the 6th term, I know I'm going to need the 2 previous. I need to add together the 5th and the 4th. So my 5th term is 5, my 4th term is 3. Adding that together, that means my 6th term of the sequence is going to be 8. Okay. So it's often possible to find algebraic formulas that are similar to what we had done in exercise 1. Okay, and so it says recall the domain that you mapped will be the set starting at 1. Again, no zeros for this. So in other words, we are trying to find some formulas here. And again, it's always a good idea to try and look for patterns. And a lot of times we want to maybe find what the first term is of the sequence to help us out. So for instance, in this first one, I know that 4 is my first term. So I could say here, my first term is 4. And I know it looks like, knowing that that's my first term, I'm constantly adding 1 each time. So if I know my first term is 4, I could say, well, to get to my next term then, to define it according to knowing my first term is 4, I could say all I need to do is add on 3. So if I wanted to have, let's say, my next term, okay, so I could add on, I'm sorry, not 3, how about 1? So if I know my first term is 4, to find my next term, I would add on 1, I'd get 5. To find my next term, I'd add on 1, I'd get 6. Okay. Letter B. So again, we're starting here and I'm trying to see what am I finding, what's going on here. So I could say like 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. That's one option. So I'm multiplying each successive term by 2. But now I have to think, okay, multiplying them all by 2, that's really like saying another thing would be 2 times 2 is 4, 2 times 2 times 2 is 8. In other words, 2 to the third power, 2 to the fourth power. So this here I could write as 2 to the n. And again, if n is 1, being our first term, 2 to the first power is 2. If n is 2, being our second term, 2 to the second power is 4, and so on and so on. Okay. And some of these, again, some of these are going to take practice. I'm going to do letter C with you and then let you try D, E, and F on your own and see how well you can do with these. For this one, I'm kind of noticing, even though that 1's not written there, it kind of looks like our denominators are increasing by 1, but my numerator is staying the same. And that's giving me that idea that my denominator just needs to change. Knowing that, again, n is 1, my first term here should be 5 divided by 1, which is 5. My second term, 5 divided by 2, which is 5 halves, and so on and so on. So trying to find those patterns. Okay, I'm going to leave these next 3 for you to try. And if you have questions, let me know. And then for number 7, our last one, it says, which of the following would represent the graph of this sequence? Biggest thing here that we have to keep in mind is, remember, when we're starting, n is always starting at 1. So if we try and solve for n of 1, that would say 2 times 1 plus 1. So 2 times 1 is 2 plus 1 would get us 3. So that means when n is 1, we get out a 3. Okay, if we tried the next one, if I tried a sub 2, multiplying these together, 2 times 2 is 4 plus 1 is 5. So again, when n is 2, I get out a 5. And notice how I'm just getting, again, integer values. So integer values means it can't be 2, and it can't be 4. I can't have them collected. But notice again, our starting value with n being 1. It was not n being 0. So that means it has to be choice 3. We're going to get something that looks like just almost like a scatter plot. We could call these a discrete graph if we were to plot these values out. Okay? Bring any questions you have to class. I will help you with this, and I hope you guys have a great day.